Here is the JPL Senior Design Group, and our project is on a low-cost submersible digital holographic microscope for in situ microbial imaging. My name is Alex Ramirez, and I'm joined here with my partners, Ben Schierman, Lihao Zheng, Brandon Dalporto, Lena Belvin, Tyler Burch, and our mentors are Andrew Mullen from Georgia Tech and Kent J. Wallace from NASA JPL. So a little bit about what our project is and what it entails. We're building a low-cost submersible digital holographic microscope to take images and volumetric data of specimens in the marine ecosystem. And so essentially what a DHM does is it allows us to take these volumetric 3D images instantaneously. And we're adding some different techniques of AI and machine learning to help us track and detect the different particles within our sample chamber of our instrument. And so overall, our project aims to reduce the overall costs of the instrument itself, the microscope, by lowering the cost of the optics and the optomechanics that hold all these optics together, as well as saving costs on how much our camera and electronics are costing us. And so we are essentially redesigning some of the previous DHM submersibles done by our mentor, Andrew Mullen. And he's worked on this project called IceFin. Here, as you can see on the top left image, that's IceFin, and he put a submersible DHM on that. We're essentially making a new instrument based off of this and the designs of the DHM from JPL to be a standalone submersible digital holographic microscope that can go up to depths of 30 meters. And so some of our stakeholders for this device are like astrobiologists, marine biologists, and climate scientists, people looking to use some type of microscope and take data at the source where these bacteria and plankton live. And it has applications of robust underwater data collection, as well as being able to mount on a device like the Blue Rove 2, as well as provide accelerated bacterial and disease classification.
So our main goal of this whole project was to reduce the overall cost of the DHM, as Alex mentioned. So we have a design requirement for the optical elements to be less than $1,000. And this includes an onboard camera, which is capable of 1 micron spatial resolution. So on top of that, the data has to be collected in situ, which means in the ocean environment at a depth of at least 30 meters for an operational time of over 2 hours. On the machine learning side of things, our design requirement is to achieve high resolution capture at 7 frames per second and be able to detect and track at least 50% of the images that we collect. And then finally, the data collection has to be autonomous.
And for our project, we've organized it into 5 different subgroups, each having their own goals for their project. Our optical group, which is Alex, is concerned with the development and integration of the microscope within the submersible. And Ben and Lena are working on the mechanical side, which are focused on developing the enclosure for our submersible and the layout of all the devices that have to go inside of that enclosure. Lihao and Alex are also working on the electronic system, which is focusing on implementing the computer system, sensors, and ensuring the functionality of all the devices for 2 hours from a single rechargeable source. And for machine learning, that's Tyler and myself, Brandon. We are working on methods for tracking and detecting areas of interest from samples and reducing our data size from collection to optimize performance and data collection capabilities on board.
Okay, so here's our overall design. Starting on the right, you can see we have our laser housing, which consists of a 405 nanometer laser diode that's powered by a 9-volt battery that shines towards our camera, which is on the left. So this laser is collimated with the collimating lens before traveling through our first optical port seen in the middle. And then it goes through a sample chamber containing ambient ocean water where our specimen will be, and then through another optical port leading the light path into our optical housing. And this is the housing that you see on the left. But this allows us to essentially shine our beam path to our camera and through ocean water, which is where our specimen is going to be. The light then travels through a series of lenses within the optical chamber where it will then be refocused onto our camera, which is the ArduCam MT9J001. So as you can see in the optical housing, we also have a wide range of electronics, including a Raspberry Pi, which is serving as the onboard computer, and a Google Coral TPU accelerator. We also have an OpenUPS, which is our battery management board that is powered by a LiPo battery, and various sensors on board, internal and external, including pressure sensors, humidity sensors, and depth sensors. And all of this is enclosed by a 4-inch acrylic tubing to maintain its watertight integrity.
So now we're going to kind of go into a few of the status updates of our subsystems. So here's for the optical system. On the very left, you can see our desktop assembly that shows our actual optical system, the bottom being the laser and laser collimation section, leading up to an optical port, a resolution target, another optical port to simulate what we'll be looking through in terms of in the actual water, having the actual optical ports there. Then it leads up to our actual optical system that contains our objectives, relay lens, and camera. So here in the middle, you can see some tests we've done showing the resolution target we have here on the left picture on the center now. And that shows our ability to get up to 1 micrometer resolution. Just next to that picture on the very right top, you can see a little video clip here of us refocusing an image that was taken out of focus. And this is done through digital processing. And that's part of the beauty of our DHM is you can refocus images and go to different Z planes if an object travels out of our focal plane. On the bottom here, we have our collimation test where we were successfully able to collimate perfectly our laser diode. And it was done here by the shearing interferometer plate. And so all of our optics have been successfully aligned and now implemented into our device.
For the power and the electronic system, we have already finished the design phase, and currently we are testing each subsystem individually. As we can see from the image A and B, we performed a stress test on the Raspberry Pi 4 as our preliminary power test. Four types of important data were extracted: the CPU ambient temperature, battery cell voltage, power usage, as well as the CPU frequency. This test gave us a rough approximation of the power consumption of the entire system. On the right, you can see from the figure C, we have integrated our sensor subsystem with an Arduino microcontroller to test the performance of the assembled sensor perf board. The next step of our power and electronics subsystem will be obtaining the real-time power consumption of the entire system after the assembly and the design of PCB that integrates the entire sensor system.
The mechanical systems were created using this, this custom optical mount, which was machined to hold the optical port, which you can see in the first picture, and fit against the 3D printed sample chamber holder. The optical mount fits against the end cap, which is seen in the middle picture, which was also custom machined. That's made from anodized aluminum. All of the components can be seen in the far right picture inside the Blue Robotics housing. We performed a depth test on this to ensure that there was no water leakage, and it was successful. The electronics tray is made from Garrett G10, which ensures that the electronics won't melt the electronics holder inside the chamber.
Okay, so for machine learning and object tracking, we were able to follow this workflow on the bottom right to train a pre-existing neural network model on our data, and we were able to detect well over 50% of our regions of interest in each image. So right now we're utilizing a Raspberry Pi 4B computer with a Google Coral Tensor Processing Unit USB accelerator to process images taken by an ArduCam monochrome camera and perform detections and tracking. So right now we're making detections at about 1.5 frames per second, which is a lot slower than our goal of 7 frames per second. But we're working on developing a new Keras model with quantized aware training to take full advantage of our Google Coral and speed up that process dramatically. On the object tracking side, you can see the red path seen in this GIF. We're able to track the centroid of each bounding box frame by frame with little occlusion and very accurate results. So yeah, in the future, we're going to continue to work on the speed, but right now we have great accuracy and good tracking.
Our plan for this semester can be divided into 3 phases. The first phase includes integrate our subsystem into submersible enclosure and perform the test on each subsystem individually. In the second phase, we'll perform the testing on the integrated system and perform a design revision and improvements. And our last phase will be performing the field test with sample chamber and a submersible pump and integrate the entire system with our Blue Rope 2. Which you can see on the image B. And currently, we have already finished the phase 1, and we are halfway on our phase 2.
So thank you guys so much for coming and watching our talk. We will be available in the listed days for questions and any thoughts you might have on our project and the subject in general. Thank you, everybody.